Welcome to Linear Algebra section 1.4. Today we're going to talk about translating between systems of linear equations, augmented matrices, and matrix equations. We'll also relate the existence of solutions to linear combinations, spans, and pivots, and we'll understand and use properties of the matrix vector product A times X. So first of all, if we have an m by n matrix A with columns A1 through AN, so we can write out each of these AIs gives us a column, and then we have some vector of numbers x1 through xn in Rn, well, then the product is given by taking the first column of A and multiplying it by the first entry in our vector in Rn. And so we have x1 times that A1 column, x2, and then we take our next piece, x2 times A2, and so on, adding them all up together. And just so you can really see the sizes, so A here is m by n, and then we're working in Rn, so this is n by 1 vectors, and this kind of makes sense because we're matching each column from A up with a row in X, so we need the number of columns to match the number of rows in order to multiply by this. And then what ends up happening is these columns kind of get absorbed, and in our result we get the number of rows times the number of columns, times 1, because each of these vectors A1 is an m by 1 vector, and we're adding up a bunch of m by 1 vectors. So let's just see this in action. So here we have a system of equations, and we're first asked to translate this into a vector equation. And so you can kind of see that we see a bunch of x1s all multiplied by something. Really, they're multiplied by, I guess what we really care about is the thing that x1 is multiplied by, this 4, 3, and 5. And so we can write that as a vector, 4, 3, 5 times x1. Then we can do the same thing for the things multiplied by x2. Now, one thing you should notice is that top equation doesn't have an x2. Well, that's the same thing as doing 0 times x2. So now we can translate down that vector to 0, 3, 7 times x2. And then finally, we have, again, same trick, 5, 7, 0 times x3. Oops, that's a 5. And the right-hand side, we can write down exactly as it is. So this is our B. That's our vector B. Okay. So now let's further translate this. And by the way, this format right here is exactly the format given in the definition. We typically put the x1 to the right of our vectors, whereas your definition, I followed the way it's listed in your book with the x1 first and then the a1. But when we're multiplying by a constant, it just multiplies each entry of your vector by that constant. Okay, so now we want to go kind of, it's almost like going backwards in this equation up here. We want to go from this vector equation to this matrix equation. And so this is called the vector equation. And here we have the matrix equation. So now we want the matrix equation. Well, what we do is when we're looking at these vectors that we've written down in step 1, that first vector is our A1, the second vector is our second column, and the third vector is our third column. And so we wind up with the first column, followed by the second column, followed by the third column, and then that's multiplied by our x vector, and we get out our b vector. So that is our matrix equation. And now we have a couple of questions about these. So first of all, what needs to be true about the pivot positions of an m by n matrix A so that ax equals b has a solution for every b? And one thing you want to keep in mind here is that we're talking about the matrix A. So we have A times X equals b. So we're talking about the coefficient matrix. So this is our coefficient matrix. We have talked about the augmented matrix in the past, and that would be when we had that column of b's added onto our matrix. But in this situation, we're just looking at our coefficient matrix. And if we think about when we could have a problem, well, the only way we have a no solution is if we have a row that ends up with something non-zero. So in other words, we have a row of zeros in A that we need to multiply by some value xn that ends up giving us something non-zero. And that's not going to make sense because it's 0 can't equal non-zero. But this happens only if we have a row of zeros in A. But remember, our pivot positions are first non-zero entries. And so in this situation then, in order to have a solution, we need to have a pivot position in every row. So in other words, we need to avoid having a row of zeros. If we can do that, then we will have a solution for every b. So now I want you guys to pause your video and think about what needs to be true about the pivot positions for it to have, this time, a unique solution. So only one solution. And my hint on that is think about what happens with the variables. Okay, so now let's talk a little bit about what can happen if we have, so we have a statement that says the equation ax equals b has a solution if and only if b is a linear combination of the columns of A. So if we think about what that means, so the idea that b is a linear combination of these columns, what that's telling us is that b must equal something times the first column of A. Because remember, we like to write A as a set of columns. Okay, so we have b equals a constant times our first column plus a constant times our second column all the way out to some constant times our last column. But actually, if we take that and maybe we'll move our b over to the other side so it looks more like our vector equation, we can rewrite this into a matrix equation where we have A1, A2 through AN times C1, C2 through Cn equals B. But now this vector C1 through Cn is a solution to the equation A times X equals B. And in case you're really unclear about that, what I mean is our X vector is the vector C1 through Cn. Okay. Let's look at a concrete example where we get into a little bit more row reduction. So let's say we have this matrix A and a vector that we're not telling you what the b values are. And we want to show, in fact, that in this particular situation, we could find values of b for which we have no solution. And let's think about how we might go about doing that. Well, in order to find a solution, we generally need to take our augmented matrix and start row reducing. So let's do that. We have B1, B2, B3. And we're going to row reduce. So let's first take our third row and add 2 times our second row. So that's going to give us, let's see, 0, -1 plus 4 is 3, 3 plus 0 is 0, and then in our right-hand column, we have B3 plus 2, B2. And then let's go ahead and try to get a 0 in that first column of our second row. So now we can take row 2 and add to row 1 to it. So our row 1 will stay the same. Our row 2, now we take 2 times row 1. So that's 2 times negative 2 is negative 4 plus 2. It's negative 2, negative 2. And then this is B2 plus 2 times B1. And then I messed up on row 3 because we had 3 plus 0. So that should have been a 3. And actually, I'm going to go ahead and make that row a little bit nicer. Let's go ahead and divide row 3 by 3. And so we get 0, 1, 1. And now we have B3 plus 2B2. Since we divided the whole row by 3, we need to divide that last, the entry in the last column by 3 as well. Okay, so we have a little bit more work to do. We can take row 2 and take row 3, let's see. Oh, let's do row 2 plus 2 times row 3. This is a little bit of a weird order to do things in, but since we haven't seen a lot of row swapping, I don't think it's so bad. So we do row 2 plus 2 row 3, and what you'll notice is we get a row of zeros right there. This matrix is not yet in echelon form. And so let's see, then we get B2 plus 2B1 plus, and then we have 2 times this thing here, okay? And then our last row stays the same. Now this is not yet in echelon form because to get to echelon form, we'd need to do the swap row 2 with row 3. And we'll go ahead and do that, although technically we wouldn't need to do that to see what's going on here. But as I said, just to give that example, so we have 0, 1, 1, B3 plus 2B2 over 3, and then finally 0, 0, 0, and then a whole lot of stuff. B2 plus 2B1 plus 2 times, hopefully you guys can see that, B3 plus 2B2 over 3, kind of squished over there. Okay, but the point here is that if we want to figure out how we can get no solution, well, basically, anytime that thing on the right is not 0, then we have a problem and we have no solution. So if B2 plus 2B1 plus 2B3 plus 4B2 over 3 is not 0, then we have no solution. And if that is 0, so if we take this guy and set it equal to 0, then we will have a solution. If we have B2 plus 2B1, all this stuff equal to 0, then we will have a solution because even though there's no pivot in that last row here, we have the equation a bunch of zeros equals 0. So remember, we saw earlier that we needed a pivot in every row if we wanted a solution for every B. But in this situation, we're saying we can have a solution for certain B's, even if we don't have a pivot in every row, as long as those B's wind up giving us a 0 anytime we have a row of A with no pivots. And in particular, one solution that we get is if B1 equals B2 equals B3, then we have a solution. But there are other possibilities. And so that's something good to try, is see if you can find another value of B1, B2, and B3 that give you a solution. And you just need to find any values that satisfy this equation here. Okay, so our next quiz asks you, which of the following is an example of an augmented matrix? So these are augmented matrices. Maybe I should make sure that is very clear by drawing our lines here. And we're looking for one that has a pivot position in every row. And so that's every row of the augmented matrix. So in other words, this does count as a pivot position in row 2, even though it's in the kind of that extra spot. And we want an example of one of these that does have a pivot position in every row, but the underlying solution, the underlying system is not consistent. Okay. Now, kind of as a similar question, we want an example of an augmented matrix with a pivot position in every row, but so that the system is consistent. Well, there's many of these, in particular that very first one. So hopefully you didn't choose that first one as your example. We have a pivot position in every row that is consistent. So pivot position in every row might be inconsistent, might be consistent, but what you should notice is those pivot positions happen in A and not in that extra bit. Okay, finally, we're going to talk a little bit about matrix multiplication. This is kind of the same idea as what we talked about at the very beginning. We have a matrix times a vector, and what we do is we take the first entry of our vector times the first column of our matrix plus the second entry of our vector times the second entry of our matrix, and then the third entry of the vector times the third entry of the matrix. And so we multiply these through and we get 1, 3, 2 times the vector 3, 2 is going to give us 2 times 3 on top and 2 times 2 on bottom. And then the next one is multiplied by 1. And when we add them all together, we get, let's see, 7 minus 4. So we do 1 plus 6 minus 4, 3 plus 4 plus 1. And that ends up giving us a 3 and an 8. And our final quiz says if we have an m by n matrix, what must be true of the vector x? So basically, what is the size of the vector x? And with that, we'll stop.